This video is about finding maximum and minimum values for a function using calculus. And I'm going to do a few questions here. The first two are just kind of conceptual. Sketch the graph of a function that has an absolute maximum but no absolute minimum. And sketch the graph of a function that has two local maxima. They're just playing around with the concepts, making sure that you understand what these words mean. And here we're going to find the critical numbers of a function. And the last thing we're going to do is find the absolute maximum and blah, blah, blah. We're basically going to use the closed interval method on that curve. All right, so let's start with the first one. So sketch a function on the interval from -1 to 2. So let's call this -1 to 2 here. That has an absolute maximum but no absolute minimum. And this should be setting off alarm bells because you have the extreme value theorem, which says that if a function of a certain kind is defined on a closed interval, then it has to have an absolute maximum and it has to have an absolute minimum. So how are you going to answer this question? The reason that this is answerable is because the extreme value theorem has certain assumptions, such as in particular that the function is continuous. So we can do this, but we're going to have to do it. We're going to have to make a discontinuous function. All right, so how can we do it? Let's say it starts there and ends there. So we want an absolute maximum, but no absolute minimum. Okay, so let's just let this be our absolute max. And then we want it to get arbitrarily small. This is kind of a lazy way to do it. So let's say that the function has a discontinuity at 1. It jumps up there like that. Okay, so now you can just see from the picture that the absolute maximum happens right here, but there is no absolute minimum because it gets as close to this value as you want. And if you want this missing value to be 1/2, let's say that it's 1/2. I'm just making things up a little bit. So this thing gets arbitrarily close to 1/2, but it never actually reaches a minimum. And so this is a legitimate answer to the question. Now let's answer the second question. Sketch the graph of a function that has two local maxima, one local minimum, and no absolute minimum. And it doesn't say that we have to do it on a closed interval, so I'll just try to make it defined everywhere. So it has no absolute minimum, so let's just make it come up from -infinity. So that'll take care of that. I'm going to turn off my, well, that's good. Okay. So it has no absolute minimum because it goes off down to -infinity, whatever's down there. And we want it to have two local maxima, one local minimum, and no absolute minimum. Alright, so there's a local maximum, there's a local minimum, there's a local maximum. And now there are lots of things we could do, but just to be obnoxious, I'm going to go off to a horizontal asymptote there at -1. So you have some freedom. So if you don't like that, come up with your own obnoxious graph. And let's just check that this meets all the requirements. So it has 3 critical points, that's flat places. It approaches a flat point here on the asymptote but never reaches one. So there are 3 critical points. 2 of these are absolute maximums. Two, well, yeah, they are, aren't they? They're absolute and local maximums, and because they tie. Let's say I'm just assuming that they're exactly the same height. At any rate, they're definitely both local maxima, and this one is a local minimum, and I have satisfied all the criteria. I think you'll agree. Let's go on to this. So finding the critical numbers really means take the derivative, set it equal to 0, and solve. If the function is not just a polynomial, you also want to keep your eye out for places where the derivative does not exist. And if you find one of those and it's in the domain of the function, then that's another kind of critical number. But for the most part, you just take the derivative, set it equal to 0, and solve. 12x equals 0. Wow, all those 12s. So we're going to solve an equation here, so don't need the 12s. So let's just write it again without the 12s. So when did I do that? Is that because you can always just disregard 12s? Is that some mathematical law? The reason that the 12s disappeared is because I divided both sides by 12, and 0 divided by 12 is still 0. So now let me factor out an x, and you have x squared plus x minus 1 equals 0. And now let's see if we can factor this part in our head. So are there two numbers that multiply to minus 1 but add to 1? I can't think of any, so let's use the quadratic formula on this part. So we'll do minus b plus or minus the square root of b squared minus 4ac divided by 2a. So we have minus 1 plus or minus root 5 over 2. And great, so those, these are really two critical numbers. So the critical numbers are these two together with 0. So let me just write them all. So 0, minus 1 minus square root of 5 over 2, and minus 1 plus square root of 5 over 2. Those are the three critical numbers. Great. So that part's done. By the way, these are the places where the function can turn around. And as a matter of fact, I graphed this function over here on the other side of the screen. You can see that it's the same. And you can see what these values mean. So here is the critical number tells you that this is a candidate place for a local extreme, and indeed this function does have a local extreme at 0. And this must be negative 1 plus square root of 5 over 2, and this must be negative 1 minus square root of 5 over 2. So in this case, all of our critical numbers give local extremes. Okay. So now find the absolute maximum and absolute minimum values of f on the given interval. So now we're using the closed interval method. So the way this basically works is that critical numbers together with endpoints. So critical numbers together with endpoints give all candidate locations for absolute max and absolute min. So the first thing we're going to do is we're going to find the critical numbers, throw in the endpoints, and this set of things will give all the candidate places where the absolute max or absolute min could occur. Then we're going to just check them one by one, and the biggest one is going to be the absolute max, and the smallest one is going to be the absolute min. That is the closed interval method. We have to take the derivative. So we have 6x squared minus 6x minus 12 equals 0. And divide through by 6, and you get x squared minus x minus 2 equals 0. And two numbers like this, positive 2 and negative 1, right? So x plus 2 and x minus 1 equals 0, and that means the critical numbers are negative 2 and negative 1. Oh, one of these was, sorry, I made a mistake. Which one of these is supposed to be negative? Negative 1. So that means that positive 1 is the solution. Okay, so we have the critical numbers, and now we need to make a list of the candidates. So that's the critical numbers and also the endpoints. So negative 2 is both a critical number and an endpoint, so there's no reason to write it twice. Now let's check the value of f at each of these locations. And if you're a really lazy person like me, then we could do it like this: 2 times x cubed minus 3 times x squared minus 12 times x plus 1. Now let's just check all these values. We need to check f of minus 2, we need to check f of 1, and we need to check f of 3. Okay, so the biggest number that came up is -3. So the absolute max, now Windows has decided to start being weird. So the absolute max is -3, and the absolute min on this interval is -12. So this occurs at x equals -2, and this one occurs at x equals 1. So let's plot this thing, just to sort of double check. So we'll plot f on the interval that includes all these things. So let's go from -2.5 to 3.5. So here it is. And let's just do a sanity check here. So the absolute, oh, something funny happened, didn't it? The absolute max is definitely not -3. What have I done? Did I enter the function wrong up here? That's probably the thing I did. So 2 times x cubed minus 3x squared minus 12x plus 1. No, that's right. And did we get the critical numbers right? We said, oh, shoot. Yeah, here's the problem. See the problem? It is that when I had that brain hiccup earlier, shall we say, I changed the wrong sign, so this should be +2, and this should be no, this should be -2. And this is embarrassing. I think that I have a carbon monoxide leak in my apartment. So that should be minus and that should be plus. So that means the critical numbers are +2 and -1, and that means the candidates are 2, -1, -2, and -3. So let's check them again. And we don't need to check 3 again. Wait, why did I write -3? I'm sorry you guys have to put up with me. I'm so ashamed of myself. So this is +3, and so now everything is good. So we don't need to check +3, we don't need to check -2. We did make a mistake here. We evaluated +1 instead of -1. And I just made it angry. Okay, so that is 8. And we also need to evaluate f of +2. So that gives -19. So now let's do a little sanity check. So it looks like the absolute minimum should be -19, and that should occur at 2. Yes, that looks very plausible. And it should be true that the absolute max is 8, which occurs at -1, and I believe that too, right? It looks good from the picture. So the absolute max is 8, and that occurs at x equals -1, and the absolute min on this interval is -19, and that occurs at x equals 2. And God, I forgot to write the negative here again. I'm going to go to the neurologist. That is the end of this video.